some examples of relations and functions. I request before this, or you should have with you the important points of relation and function so that you can easily see if it is required. So let us take one example. Hello friends, let us solve some examples of relations and functions. I would request that you keep the book or the page where you have written important points of this chapter so that if it is needed you can see that. Let us begin. So you are having a relation S and you are given like this 1 1 2 2 3 3 4 4 5 5 on a set A equal to 1 2 3 4 5. Then the question is, what type of relation is this? The options are symmetric only, then second option reflexive only. Now only means if it is reflexive only, then it should not be symmetric or transitive, okay? Then transitive only, and an equivalence relation. Friends, we know if a relation is reflexive, symmetric and transitive, then it is an equivalence relation. Now, looking to this S 1 1 2 2 3 3 4 4 5 5, so surely the reflexivity is there, because what is reflexive? It is like this: XX belongs to S for all X belongs to the set A. Now what is symmetric? So symmetry is like this: if, so do take care, if, okay, so if XY belongs to S, then YX also should belongs to S. Here in this S, we know that XY belongs to S, so 1 1 belongs to S, okay, or 1 1 also belongs to S, so this symmetry is surely satisfied. And similarly transitivity. What is the transitivity? Here also, if XY YZ belongs to S, then XZ also belongs to S. So here this condition is also satisfied here in this S. So our answer is it is an equivalence relation. Okay. So D option is there. Let us take one. If A equal to 1 2 3, then the number of equivalence relation So number of equivalence relations containing one, two is blank. So how many equivalence relations are there? One is set A 1, 2, 3, which contains the element 1, 2. So the options are 1, 2, 3, 8. So let us take one equivalence relation which contains 1, 2, one is set 1, 2, 3. So it must be reflexive, so we should write to 1, 1, 2, 2, 3, 3. This is surely. Now it must contain 1, 2. So these many elements must be there. Now to make the equivalence relation, the symmetry should also be there. So this 1, 2 is there, so 2, 1 also there. And if I close this set, this is an equivalence relation. So we get one equivalence relation. Let us try for another. So 1, 1, 2, 2, 3, 3, 1, 2, 2, 1, and let us add one more point, say 1, 3. So if I add 1, 3, I must need to add 3, 1 also because of symmetry. Now transitivity is also there. So here 2, 1 is there, 1, 3 is there. So because of the transitivity, I need 2, 3 also in the set. So 2, 3 should also be there in the set. Once 2, 3 is there, and because of symmetry, 3, 2 should also be there. So, and now there is no other element left in A cross A. So this is the universal relation. So naturally now there won't be any more relation, equivalence relation containing 1, 2. So the answer is 2. So there will be 2 such equivalence relations which contains 1, 2. Okay. S is defined on Z by xy belongs to S double implies modulus x minus y less than or equal to 1. Question is, S is blank. So options are reflexive and transitive, but not symmetric. Another option, reflexive and symmetric but not transitive. Then symmetric and transitive but not reflexive. Fourth option, an equivalence relation. Now here we see that we are having xy belongs to the relation S if and only if modulus x minus y less than or equal to 1. In short, you can say also that distance between x and y is less than or equal to 1. Now, reflexive is sure there because that is easy to see. Xx surely belongs to S for all x as modulus x minus x equal to 0, and that is less than or equal to 1. So reflexive is there. Symmetry is also there, because modulus of x minus y is same as modulus of y minus x. So if xy belongs to S, then modulus of x minus y less than or equal to 1, but this would imply modulus of y minus x also less than or equal to 1, because modulus of x minus y is same as modulus of y minus x. And that means yx belongs to S. But see, the transitivity is not there, because the distance between x and y is 1 or less than or equal to 1. So if I select say x equal to 1, y equal to say 2, z equal to say 3, then xy belongs to S, yz belongs to S, because distance between them is 1. Modulus x minus y is 1, modulus y minus z is 2. But see, what is modulus of x minus z? That is 2, and that is not less than or equal to 1. Therefore xz is not in S. That means transitivity is not there. So reflexive and symmetric but not transitive. So this B option is the answer. Okay. If S is defined on R by xy belongs to S, if and only if product xy greater than or equal to 0, then S is blank. So the options are an equivalence relation, then another option is reflexive only, then symmetric only, and transitive only. Okay, so S is defined on real number R, on set of real numbers R, that xy belongs to S double implies the product x and y greater than or equal to 0. See, reflexivity is there, because we know product xx is x square and is always greater than or equal to 0. So this would imply xx belongs to S for all x belongs to R. So symmetry, reflexivity is surely there. Okay. Then symmetry, that is also there, because if xy greater than or equal to 0, that means say if xy belongs to S will imply xy greater than or equal to 0, but xy is same as yx in real number, so yx also greater than or equal to 0, and will imply yx also in S. So symmetry is also there. Let us see transitivity. So in transitivity, if xy and yz belongs to S, so therefore xy greater than or equal to 0, yz greater than or equal to 0. Now xy greater than or equal to 0 is happen when x greater than equal to 0, y greater than equal to 0, or x less than equal to 0, y less than or equal to 0. Now yz greater than equal to 0. So in this situation, because y greater than equal to 0, z has to be greater than equal to 0. In this situation, y less than equal to 0, z has to be less than or equal to 0. Okay, so for yz is like this. Now what about xz? So if x greater than equal to 0, then z also greater than equal to 0. And if x less than or equal to 0, then z also less than equal to 0. So when x greater than equal to 0, z greater than equal to 0, x less than equal to 0, z also less than equal to 0. So in short, xz is always greater than equal to 0. That means xz belongs to S. So it satisfies all three: reflexive, symmetric and transitive. So the answer is S is an equivalence relation. So S is an equivalence relation. Okay. Next, which of the following defined on Z is not an equivalence relation? Option A, xy belongs to S if and only if x greater than or equal to y. Second option, xy belongs to S if and only if x equal to y. Third option, xy belongs to S if and only if x minus y is a multiple of 3. And fourth option is xy belongs to S if and only if modulus x minus y is even. Now looking to this all four relations, we can easily see that this should not be the symmetric. This relation should not have symmetric, because if xy x greater than equal to y, you cannot say that y greater than or equal to x. Okay, so this relation A is not symmetric, and therefore A is not an equivalence relation. So here A is the answer. Okay, so this has no symmetry. Okay. Next, let us see S is defined on n cross n by this way: AB and CD. These two elements from n cross n are in relation, that means belongs to S, if and only if A plus D equal to B plus C. Then S is reflexive but not symmetric. S is reflexive and transitive only. S is an equivalence relation. And S is transitive only. Now see, here two elements are like this, AB, AB, and that is belongs to S. For all AB belongs to N cross N, because why? So if AB belongs to S, then it should be like this, A plus D. So here A plus B equal to B plus C. So B plus C. So here also it should be B plus A. And that is true in natural number. So this is reflexive. Okay. Now if AB, CD belongs to S, then it is A plus D equal to B plus C. We would like to check the symmetric. And for symmetric, we need CD AB belongs to S, like this. Okay, and when does CD AB belongs to S, the result is like this. See here, A plus D. So here C plus B. So let us write here C plus B. Then it should be equal to B plus C. So here also it should be equal to D plus A. And can you say from this to equal? Answer is yes. Okay, and so this is in S, and therefore S is symmetric. So it is reflexive and symmetric. Now see, if you are little smart, there is no such option having reflexive not symmetric. So this A is not there. Is reflexive and transitive only, but symmetric is already there. So this also not a correct option. S is transitive only is also not a correct option because it has symmetric as well as reflexive. So it's natural that it should be having C option. It must be equivalence relation. So you can save the time also. Just stop here, see the options, eliminate the options, and then give the answer so that you can easily. So we don't prove here it is transitive, but just looking to the options you can easily check them. Okay, so C is the option. Okay, let us take one more. Let S be the relation on the set A equal to 5, 6, 7, 8. So defined like this: S equal to 5 6 6 6 5 5 8 8 5 7 7 7 7 6. Then options are S is reflexive and symmetric but not transitive. Second option, reflexive and transitive but not symmetric. Third option, symmetric and transitive but not reflexive. And fourth option, an equivalence relation. Now see, the set is 5 6 7 8. We are having 5 5 6 6 7 7 and 8 8 also. So S is reflexive. Reflexive, sure. Okay. See whether symmetry. So 5 6 is there. Does 6 5 is there? So let us scan. Not there. That means S is not symmetric. As 5 6 belongs to S, but 6 5 is not in S. Okay. So reflexive, not symmetric. Reflexive and symmetric. So this option is not there. Reflexive and transitive but not symmetric, that might be there. Symmetric and transitive but not reflexive, so this option definitely not there. Equivalence relation, no equivalence relation, so this option is also not there. No need to check anything else. Now B is the correct option. Okay, so B is the correct option. S is given like this: 1 2 2 3 on A equal to 1 2 3 to make S an equivalence relation, at least blank order pairs are to be added. So options are, means 5 pairs need to be added. How many pairs to be added so that this becomes an equivalence relation? 6 3 7. Now to make the equivalence relation, these two elements should be there inside the set. So 1 2 2 3 already there. Now let us see how many pairs we need to add. So for reflexive you must need 1 1 2 2 3, 3. For symmetry, you need 2, 1. You need 2, 3, 2. Now for transitive also, see, you are having transitive, you are having say some pairs like 1, 2, 1, 2, 3. So you must need 1, 3. Once you need 1, 3, you must need 3, 1 also for symmetry. And I think all the elements of A cross are exhausted here. So how many pairs are there to be added? 1, 2, 3, 4, 5, 6 and 7. So answer is 7. 7 pairs need to be added here. Okay, thank you.